So let's talk about electromagnetic radiation a little bit more in depth. So yeah, it's a scary word for some people, like I mentioned in the other video. But all electromagnetic waves is they are two wobbles at the same time, or two vibrations, if you want to think about it that way. They are a wobble in an electrical field, and they're a wobble in a magnetic field. Now, we can't just stop talking there. We got to go a little bit further in. But the electrical field has one direction, and the magnetic field travels at a 90-degree angle, perpendicular to the electrical field. And the reason that these things exist, the reason why electromagnetic waves happen, is quite simply when you move a charged particle through a magnetic field. They give off different kinds of electromagnetic radiation depending on how fast they're moving or how fast you stop them. Talk about that in a bit. So all electromagnetic radiation travels at the speed of light. It's 3 times 10 to the 8 meters per second. This is going to come in handy when we start talking about calculations that we need to be able to do. So there's really 3 components, 3 numbers that let us describe an electromagnetic wave. The first one's already taken care of, the speed. And we call that speed of light lowercase c. I want you to keep in mind this only is true for electromagnetic waves. There are other kinds of waves in the universe. You've got like sound waves, and you've got waves that crash into the shore at the beach. Those waves, you got waves where, when we get back to going to sports, hopefully sooner rather than later, because I'm really missing hockey. The wave where you raise your hands up, and then the people beside you raise their hands up, etc. Those waves travel at different speeds. But electromagnetic waves, they always travel at 3 times 10 to the 8 in empty space. And another cool thing about these electromagnetic waves, they do not need stuff to go through. Like waves in the water, they need water to propagate in order to travel. Sound waves need stuff to travel. Matter, because a sound wave is matter bumping into some more matter, bumping into some more matter, so on and so forth until it gets to your ear. And then the air, if you're listening to somebody in the air, that moving air is wobbling your eardrum, which is wobbling some bones inside of your middle ear, and bio 30, you end up hearing stuff. But these guys, they can travel through the vacuum of space, and as a matter of fact, they have to, because if they didn't travel through the vacuum of space, it would be awfully dark and cold on Earth. The sun gives us most of our electromagnetic waves. So the sun is doing fusion. It's doing this nuclear reaction that we'll talk about much more in Unit D, where you take little tiny atoms and you slam them together really hard at a super high temperature. And when you slam those atoms together really hard, the nuclei, the stuff in the nucleus, the protons and the neutrons of those 2 atoms, they stick together and they make a single atom. And you also release a stupidly high amount of energy. Most of it is EMR, electromagnetic radiation. Almost all of it, actually. So there are 3 things that we need to know about waves, or about electromagnetic waves. First of all, we know the speed of all of these waves is the speed of light, little c. We also have another value called frequency. Frequency is how often the wobble happens. Sound people, if you like listening to music, or if you produce music or anything like that, you know generally what a frequency is. It's how high-pitched or low-pitched a sound is, when we're talking about sound, obviously. So if you like listening to music that's got a lot of bass in it, and I mean most people do, it's kind of the fun part of the song, really. You might listen to some music where a drum machine like the 808 was used, and the 808 uses something very close to a sine-shaped wave. And generally, bass is around 20 to 50 or 60 hertz. And a hertz is what we call a cycle per second. And so 1 hertz equals one thing happening per second. So in the context of a wave, one cycle from top to top, crest to crest, or from trough to trough, aka bottom to bottom, per second. So the wave frequency of electromagnetic radiation is insanely high. The wobbles, these waves are wobbling really, really fast. A megahertz is a million of a thing happening every second. A gigahertz is a billion wobbles a second. And these can go up to even the terahertz. That's a trillion wobbles per second. That's craziness. But that's how electromagnetic radiation works. So we have frequency, hertz. What does it look like in a formula? F. We also have wavelength. That's the distance between 2 points in a wobble. So if I look at the top, the crest of this wave, to the crest of that wave, that is one wavelength. And wavelength is measured in meters, or the units that we make from meters, like micrometers or nanometers, etc. Nanometers is actually a really, really handy one that we use quite often because of the fact that a lot of these waves are super, super small. The distance between the top of the wave and the next top of the wave is like a couple hundred nanometers. And the formula variable that we use is the Greek letter lambda. It looks kind of like an H. It's really not, though. It's like an L. It's the Greek version of the letter L. And so there are an enormous range of wavelengths. The lowest frequency radio waves can have a wavelength of kilometers. And the highest energy gamma rays, the shortest wavelengths, can have just a couple of nanometers. So from kilometers all the way to nanometers, that's a huge range. So let's talk about how we work with these values, the speed, the frequency, the wavelength. It's really easy. Here's your formula. Speed wave is the wavelength times the frequency. So one thing that you might end up being asked is something like this. We always ask you to kind of convert between wavelength and frequency. So here is a good example. A microwave outputs EMR at a frequency of 1600 megahertz. What's the wavelength? So we look at our formula up here, V equals lambda F. And since we know this is a speed, or it's an electromagnetic wave, it's not a sound wave, it's not a wave at a beach, we know that V is the speed of light. We also know the frequency. And whenever you see big M like this, a mega, that means a million of something. So what does it really mean for us? It means 1600 times 10 to the power of 6. Why 10 to the power of 6? Because that's a million. So this is 1600 megahertz. So I need my unit of hertz. Or I could even use per second. And the reason why I'm allowed to use that is because the units are going to end up canceling out. It's going to be beautiful. Wavelength is a measurement of distance. So if we do this right, we'll be able to figure out the wavelength in meters of this wave. So we don't know that number right now. So we look at our formula, V equals lambda F. V equals lambda F. I need to turn this into a formula that has lambda all alone. We are probably really good at this now. Divide both sides by F. V divided by F equals lambda. So here's how I'm going to write my V and F. So I'm going to say 3.00 times 10 to the 8 meters per second. I know I did a slash here, but remember, when you're writing it in a formula, you really want to emphasize the fact that when you say the word per, you're doing a division line, you're making a fraction. Now I'm going to divide by this number. And here, there's going to be something a little bit strange about this, but it's going to make sense. I have 1600 times 10 to the 6. I'm going to write that down here. 1600 times 10 to the 6. What does that 10 to the 6 mean? It's the wobbles per second. And if you want to say like wiggles or waves per second, you can kind of do that. I'm just going to leave it without a unit. But since it's per second, I'm going to go per, and then second is going to go on top. Here's where the magic happens. We got a seconds on the bottom, we got a seconds on the top. We are allowed to cross those out. So all we need to do now is take our top number, 3.00 times 10 to the power of 8 meters, and divide by 1600 times 10 to the 6. Remember to bracket these on your calculator, please. If you don't, when you divide by a number that has an exponent, you're going to get some weird garbage. So I'm going to say 3.00 times 10 to the power of 8. That would go into my calculator. Then I would use the multiply key, or sorry, the divide key, my bad. And then I would go bracket 1600 times 10 to the power of 6. Then I hit my enter key on my calculator. So I'm just doing that now. 3 times 10 to the 8 divided by 1600 times 10 to the 6. And we get 0.1875. And that's in meters, if you're wondering why. Look, boom. That's the only unit that's there is meters. So 0.1875 meters, which is going to be, let's see, we have 2 sig digs according to this value here. So 0.19 meters. Or, if you want to be a smarty pants, 19 centimeters. So this is the kind of math that you need to do. It's really, 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 really simple. So I'll do one more example. I'll give you a wavelength and we'll figure out the frequency. Say, let's do a red laser. So a red laser gives off photons of wavelength 460 nanometers. What is the frequency? So we are going to identify what we have. Little n means nano. It's times 10 to the minus 9. This is also in your data book. All those powers of 10, all of the SI unit modifiers like nano and giga and tera and exo and all that, they're all in there. So you don't need to really, and micro of course, you don't need to memorize these. So my V, since it is still light energy, or it is electromagnetic radiation, we're going for 3.00 times 10 to the power of 8 meters per second. Our frequency is, I don't know. And our wavelength, I have to draw a little lambda here because I'm not fast enough with typing it. So our lambda equals 460. And if I want a nanometer, I'm just going to go times 10 to the minus 9. That's what a nano is. You can literally plug in whatever the modifier is right into the formula. I know it looks awkward and you're like, shouldn't we like change that to 4.6 times 10 to the minus 7? No, forget it. Just leave it the way it is and it'll all come out in the wash when we calculate. I promise. So V equals lambda F. Wavelength times frequency. We're looking for frequency, so we are going to divide both sides by lambda. And that lets us cross out lambda on this side. So goodbye to you. Hey, look, frequency. There we go. So we know we're doing it right. So now all I have to do is do the division. So here goes. I'll show you how to enter it into your calculator. So 3.00 times 10 to the 8 meters per second, or rather, since we're doing it in our calculator, you don't want to put units in your calculator. Just be aware of them. Divided by 460. Oops, should bracket that. Times 10 to the power of minus 9. And that's our meters. So we type that in. Divided by 460 e negative 9. We get a really big number. And yes, frequencies of electromagnetic radiation, like I said before, are really high. So if you get a brain-hurtingly high number, you're probably on the right track for a frequency. If you get a really brain-hurtingly high number for a wavelength, you goofed. The highest wavelength you're probably ever going to see is like 1,000 meters a kilometer. Most of the time, wavelengths are very tiny. So that gives us, let's see, we have 2 sig dig, so 6.5 times 10 to the 14 hertz. And you can leave it like that. You don't have to showboat and turn this into megahertz or gigahertz or terahertz or whatever. This is plenty good. So I hope this gives you a little bit of background about electromagnetic radiation. This plus the video debunking the whole cell phones causing cancer and COVID-19 being caused by 5G. Between those two, that's going to give you a pretty good background. We'll talk a little bit more about the different types of electromagnetic radiation in the reading that I've assigned to you. All right, guys. See you next week.